Okay, in this section we're going to talk about continuity and one-sided limits. Let's get started with continuity. For a function to be continuous at a point C, there can be no interruption at the graph at the point C. So below are some examples of graphs that have an interruption at x equals 5. And so each of these graphs are not going to be continuous at x equals 5. Another way to think of this is if you have to pick up your pencil to trace the graph, then you've got an interruption, and therefore you can't it can't be continuous at that number. So for this graph, notice there's a break in the graph at x equals 5. So we don't have continuity here. For this graph, we have a hole in the graph at x equals 5. So we don't have continuity at x equals 5. For this graph, we have a vertical asymptote at x equals 5, so we don't have continuity. Now here's another graph that has a hole in it at x equals 5, but the difference between this one and the one up here is that this one is not defined at x equals 5, but this one does have a value at x equals 5, and it's right there. But the difference is there's a break in the graph, because if you tried to trace this graph, you would draw this portion, and then you would have to stop and go down here and draw this, then pick back up and come up here and finish it. So there's a break in the graph. And here's another example where there's a break in the graph at x equals 5. So all of those functions are not continuous at x equals 5. Now the definition of continuity basically says for a graph to be continuous at a point C, three things have to be true. First of all, the function has to be defined at C. In other words, C must be in the domain. The limit of the function as x approaches C must exist. And then the third thing that must happen is that the limit as x approaches C must equal the functional value at C. So let's look at number 1. Number 1 up here, the graph is not defined at 5. Now I couldn't actually draw these little circles, but there's little holes, circles right here. So here the graph is not defined at 5. Let's see, number 2, also the graph is not defined at 5. So here the graph is not defined at 5. Number 3, the same thing, the graph is not defined at 5. Okay, now number 4, the graph is defined at 5. It's defined to be this point. But here, the limit is actually here at this value. So the limit is up here at 10, but the functional value is down here. It looks like it's maybe at 5. So the limit is 10 as x approaches 5, and the functional value at 5 is certainly not 10, because it's way down here. So that's why that one is not continuous at 5. Now this one is defined at 5, right? So right here. So this one's defined to be this value at 5. But if you look at this, the left-hand limit is equal to one number, where the right-hand limit is a number up here. So the limit does not exist. So in that case, the limit does not exist. So there's different reasons why a function might not be defined at a value. Now you can read the discussions here of the continuity for these three functions. This one's pretty straightforward. It's not defined at -1. This one at x equals 2, condition 2 fails because the limit as x approaches 2 does not exist. See, if you approach 2 from the left, you're actually approaching through this function, so you would get 3. 2 times 2 minus 1 is 3. But if you approach 2 from the right, you would get 1 minus 2 squared, which is -3. So the limit does not exist because you get two different values as you approach 2. So the limit does not exist as x approaches 2. And for this one, the function is defined at x equals 5, but if you actually used the replacement theorem and got this limit would actually equal 10 The limit of this as x approaches 5 is 10, but the functional value is 6. So the two are not equal. Now, the good news is, for our polynomial functions, they're continuous at every real number. And rational functions are continuous for all real numbers in their domain. And operations on continuous functions are continuous, and composition of continuous functions are continuous. So, this is a polynomial, so it's continuous for all real numbers. This is a rational function, so it's continuous everywhere except values that are not in its domain. Well, you know the denominator can't be 0, so 0 is not in the domain, 4 is not in the domain, and -3 is not in the domain. So this function is not continuous at 0, 4, and -3. This function is a composition of a rational function and a well, I said rational and polynomial, but it's actually exponential because you're raising it to a power. But basically the point is that if x is 2 or -2, the function on the inside is not defined. So therefore this function, if you try to cube it, that function is not going to be defined either. So this function is not defined at 2 or -2. Okay, let's talk about one-sided limits. So in order to discuss continuity on a closed interval, we need to talk about one-sided limits. Most of the limits we discussed previously have a left-hand and right-hand limit. So for instance, this function, as you approach 5 from the left, you'll see this function is -1, but as you approach 5 from the right, this function is +1. So we would say that the left-hand limit is -1 and the right-hand limit is +1. And notice the notation we use. We put the little negative sign here for the left-hand limit as x approaches 5, and the positive sign for the right-hand limit as x approaches 5. So the left-hand limit, this would mean the limit of the function f of x as x approaches c from the left, and this would mean the limit of the function f of x as x approaches c from the right. Okay. Now if you look to the right here, you get the graph of square root of 9 minus x squared. Well, to discuss the limit as x approaches plus or minus 3, we can only use one-sided limits. Notice that for this function, because of the domain of the function, the domain's only values from -3 to 3, so you cannot approach -3 from the left, okay, because there's no function over there, there's nothing over there, and you cannot approach +3 from the right. So to talk about continuity at these endpoints -3 and 3, we actually have to just focus on what we can approach. So what we can do is look at -3 from the right hand side and look at approaching +3 from the left hand side. So as long as the limit as we approach -3 from the right is the same as the functional value, then this function is continuous at -3, and as long as this limit as we approach 3 from the left is equal to the functional value 0, then we have continuity at 3. So if you look at those limits, you can see as we approach -3 from the left, the function goes to 0. From the right, the function goes to 0. And as we approach 3 from the left, the function goes to 0. And actually, that's the same as the functional value. So since the functional values are equal to those one-sided limits, then we can actually say that this function is continuous at -3 and 3. Okay? Now, one-sided limits bring in something that's called the existence theorem. And basically the existence theorem says, it really says this. It says for a limit to exist, both one-sided limits have to exist and be the same number. And it also says if both one-sided limits exist and are the same number, then the limit must exist and it's going to be the same number. So if you were to know that the limit of a function as x approaches 2 is 5, then you automatically know that the left-hand limit as x approaches 2 is 5, and you know that the right-hand limit as x approaches 2 is 5. So that's, sort of a given. So if you go back and think about this function up here, see, the reason this limit doesn't exist is because the limit from the left is -1 and the limit from the right is +1, and the only way the limit itself can exist, so basically we would say the limit as x approaches 5 does not exist because the two one-sided limits are not equal. So the two one-sided limits must be equal for the limit itself to exist. Okay, now moving on to continuity on a closed interval. So for continuity on a closed interval, we have to say a function f is continuous on a closed interval from a to b if it is continuous on the open interval from a to b, and the right-hand limit of the left endpoint is equal to f of a, and the left-hand limit of the right endpoint is equal to f of b. That's what I was saying up here. So the limit, this function is obviously continuous between -3 and 3, but it's continuous at -3 if the right-hand limit is equal to the functional value, and it's continuous at 3 if the left-hand limit is equal to the functional value. So that's basically what that says. So that function above there, we know that the limit as x approaches -3 from the right is 0, and that's the same as what you get at f of -3, and we know the limit as x approaches 3 from the left is 0, and that's the same as you get if you evaluated the function at 3. So therefore the function is continuous on the entire closed interval from -3 to 3. Now the greatest integer function is kind of a strange critter. It returns the greatest integer less than or equal to the input. So basically if you put in 1, it's going to return 1. If you put in 1.1, it's going to return 1. 1.5 is going to return 1. 1.9 is going to return 1. 1.99, 1.999 is going to return 1. So if you choose any number from 1 all the way out to, but not including 2 here, then you're going to get 1. So, that's 1 right there, right? But once you hit 2, and then any number from 2 up to but not including 3, it's going to equal 2. And then at 3, any number 3 up to but not including 4, it's going to equal 3, and so forth. So it's also called the step function. Now really the main reason we talk about this function is to talk about continuity. You'll notice that the breaks in this function occur at these integer values. There's a break at 1, there's a break at 2, there's a break at 3, which is right here, there's a break at 4, and so forth. So the greatest integer function is discontinuous at integers, so it's not continuous at integers. See, because let's take a look at the limit of this function as x approaches 2 from the left. Okay, so here's 2. So as we approach 2 from the left, it's going to be at this level, which is 1. But if we approach 2 from the right, we're approaching up here, and so that's going to equal 2. So the limit from the left is 1, the limit from the right is 2, so therefore the limit does not exist as x approaches 2. And since the limit does not exist at x approaches 2, then of course it can't be continuous at that point. Okay, I'll finish this section with some tests for continuity and a few other notes, but let's go ahead and shut this video off and move on to the next one.